Hello everyone from Math 1340, Statistics. It's Professor Wenson here again with a video on your KnewtonAlta homework for section 3.2 titled Independent and Mutually Exclusive Events. Now these are two separate things. We're going to be learning about what it means for two events to be independent, right? Whether or not two events are independent or dependent. And separately from that, we're also going to be learning about whether or not two events are called, mutually exclusive or disjoint. All right, so here's your KnewtonAlta, again, a preview of it. You're not going to see the exact same questions in the exact same order I am, but the objectives will be the same, the kinds of problems will be the same, all the instruction will be the same. Okay. Now this has only two objectives, this section, so hopefully a shorter one. And the first of these is understand mutually exclusive events. What does it mean for two events to be mutually exclusive? So as with most objectives, I say, when you've seen it for the first time in these assignments, click on More Instruction. You don't have to. You can work through it without the instruction if you're comfortable with the material. Let me show you this instruction here on this objective and read you some definitions. So to make calculating probability easier, we want to identify any special relationships between events. For example, if we were asked to find the probability that a triathlete is both riding their bike and swimming at the same time, we should be very skeptical. A and B, right, so remember capital letters are usually used here to represent events. Events A and B are mutually exclusive events if they cannot occur at the same time. That means A and B do not share any outcomes. Another way of saying that is the probability of, A and B. Remember, this is that intersection, A and B. The probability of A and B equals 0. Remember, when a probability is 0, that means it cannot occur, it cannot happen. Meaning, so in a Venn diagram, there is nothing in the overlap. There is no overlap. So very often, instead of writing an empty overlap like this, they'll just draw the circles so that they're separate. So here in this picture, events A and B are mutually exclusive. They don't share anything in common, any outcome in common. Whereas in this picture, events A and B are not mutually exclusive because they do have an outcome in common, this outcome of 5. All right. So be careful. Pay attention. All right. So if it is not known whether A and B are mutually exclusive, assume that they are not until you can show otherwise. Assume that they do have something in common, some overlap, until you can prove otherwise. All right, so another reading here of the definition and then an example. So suppose you have a fair, well-shuffled deck of 52 cards, right, a standard playing deck. It consists of 4 suits. Right? You have clubs, cards, diamonds, hearts, and spades. There are 13 cards in each suit, right, consisting of 2 through 10, then a jack, a queen, a king, and an ace of that suit. Right. So we're given the events A and B below. Right. The question is, are the two events mutually exclusive? So you see event A is choosing a jack, and event B is choosing a card choosing a spade. So if you're asking, are they mutually exclusive, that's asking, do they have any outcomes in common? Can these happen at the same time? And yes, they can, you can have a jack that is also a spade, right? The jack of spades. So these events share an outcome, the jack of spades. So these events are not mutually exclusive. All right, see, they are not mutually exclusive because they share a possible outcome, the jack of spades. If they don't share an outcome, if they can't happen at the same time, that's when the events are mutually exclusive. Okay. All right, so then I'll do a problem like this in a minute. You can read through this on your own, and another key term here. Now, another word for mutually exclusive is disjoint. Can also be described as disjoint events. So saying that two events are mutually exclusive and saying that two events are disjoint means the same thing. All right, so here's a question. So you have a fair die with 6 faces containing the numbers 1 through 6. So we're given events A and B. Are the two events mutually exclusive? All right, so I'll pull up some paper here. I know you can probably tell already. But event A is rolling a 1 or a 2. So event A would contain these outcomes. And event B is rolling an odd number. So rolling a 1, a 3, or a 5. And if I were making a Venn diagram, so remember this is the universal set, or the sample space represents everything. Then I got a circle representing set A. And do you see they do share something in common? I'll draw a set B, right? The circle B for event B here, and put down where all these outcomes show, right? Oh, well, there is one in the overlap, right? The rolling of the number 1, and then A has a 2, but B doesn't, and B has outcomes 3 and 5, but A doesn't, But this middle part is not empty. Right, this is not empty. This overlap. So these are not mutually exclusive. So no, the events are not mutually exclusive because they both require rolling the same die. That's nothing to do with that. No, the events are not mutually exclusive because they share a common outcome of 1. Right? They both would have the number 1 in the event, as you saw in my paper. So that's the reason they're not mutually exclusive. All right, so here. We got all this about a fair die, 6-sided die. All right, so event A is rolling an odd number, so 1, 3, 5. Event B is rolling a 4. All right, so just the set with the number 4 in it, outcome 4. And event C is rolling an even number on a fair die, so 2, 4, or 6. So given the 3 events, which of the following statement is true? Select all that applies, so more than one of these might be true. A and B are mutually exclusive. Like I said, this has the outcomes 1, 3, 5. B has the outcome 4. They do not have anything in common. They do not share any outcomes, so they are mutually exclusive. That is correct. How about events B and C? Again, event B contains the outcome 4. Event C contains the outcomes 2, 4, and 6. They share the outcome of 4. They have the outcome of 4 in common. So B and C are not mutually exclusive. So I'm not clicking that one. Events A and C are not mutually exclusive, meaning they do share stuff. Well, let's see. A is rolling an odd number. C is rolling an even number. They are mutually exclusive. So this is false. That's part D. The events A and C are mutually exclusive. Right? They don't share a common outcome. So they are mutually exclusive. So another question. Now this time, this is one of those interactive ones where you have to move things into the Venn diagram, move these dots here. There's R1, R2, R3, B4, B5. All right, so here we have an evenly weighted game spinner. Has 5 numbers on it, labeled and contained in a colored piece on the spinner. 3 are colored red. All right, 1, 2, and 3 are abbreviated R. 2 are colored blue. The 4 and 5 are colored blue, abbreviated B. All right, so consider the Venn diagram below. All right, so event A is spinning an even number. Event B is spinning a number greater than 3. So just 4 or 5 then, right? So then put things in the appropriate places. So an even number, now greater than 3, the overlap has a spin of a number, that's even and greater than 3. Well, the only even number greater than 3 in this 1 through 5 here is 4. So if you spun the blue 4, if you spun the 4, that's both even and a spin where you get a number greater than 3. So you see, these two events do have something in common. They do share an outcome. So these two events, A and B, are not mutually exclusive. Now over here, the greater than 3 stuff, that'd be 5, and that's it. Then the even 2, right, the red 2. The red 1 and the red 3 don't belong to either of these, so I'll keep them outside the circles, right? They're not even numbers, and they're not greater than 3. All right, so that's all the movement I need to do there. And see, they say A and B are, not mutually exclusive again because they do share an outcome. The probability of A and B is not 0, right? There's actually something in A and B. Looks like probably one more here in this objective. So a card is drawn from a standard deck of 52 cards, and they're telling you how they're made up. 4 suits, each suit has 13 cards, and what the cards are. Given the 3 events, which of the following statements is true? So another select all that apply, right? So how about B and C? Look at B and C. Now drawing a spade, and C is drawing a queen. Do they have a common outcome? Yeah, the queen of spades is in both of these. So this is not true. B and C are not mutually exclusive. How about A and B? Draw a club, draw a spade. If I pick a card, it can't be both a club and a spade. You can't have a card with two. There aren't any cards with 2 suits. So yes, A and B are mutually exclusive. They do not have an outcome in common. A and C are not mutually exclusive? Yeah, you can. That's correct. Because if you look at A and C, the queen of clubs would be in both A and C. So A and C share a common outcome, the queen of clubs. So they are not mutually exclusive. A and C is correct, and that means that the fact that this statement that they are mutually exclusive is not true. I'm not going to click on that one. All right. So hopefully you got the definition of mutually exclusive down, or disjoint, what it means for 2 events to be mutually exclusive. All right, then the only other objective in this section is distinguish between independent or mutually exclusive events given conditional probability information. All right, you've seen conditional probability notation before, right? That was the probability of event A given that event B has occurred or something, right, with a little bar. And again, this is kind of 2 separate things. One is you're going to determine if 2 events are independent or dependent. And then the other questions you'll be asked if 2 events are, mutually exclusive or not. So kind of tying into objective 1. All right, so I'll go through the more instruction again. It's the first time I'm seeing this objective. So we're asked to distinguish. All right, so remember conditional probabilities can also tell us information about whether 2 events are independent or mutually exclusive, or both. Right? Recall that if two, all right, so here's the definition of independent events. Right here that I just highlighted. Two events are independent means that one occurring does not have any effect on the other event occurring. Right. So two events are independent means if one event happens, it has no effect whatsoever on whether or not the second event happens. For example, if I flip the coin twice, the probability of flipping a head on the first flip is 1 out of 2. So say the first flip was a head. The fact that the first flip became heads has no effect on what happens on the second flip. The probability of flipping a head is still 1 out of 2. It doesn't change. All right. So if the probability of an event doesn't change when one thing happens, so if I have events A and B, if A happens and it doesn't change the probability of B, then they would say that A and B are independent. And if it does change, then they're dependent. And then they have the last sentence in this first paragraph. You already know what it means for events to be mutually exclusive now. All right, so I got that. All right, so say events A and B are independent. That means that the probability of A, given that B occurs, remember this notation here, all right, this was that conditional probability. That means the probability of A occurring, given that B has occurred, is just the probability that A occurs. All right, so the fact that B occurred has no effect on the probability that A occurs. It doesn't change the probability that A occurs. All right, so no matter what is going on with the probability of B, this goes the other way as well. All right, if the other way as well means the probability of B, given that A occurs, is equal to the probability of B. All right, so one event happening has no effect on the probability of the other one happening. And we'll get to some examples, obviously with some questions. All right, so we can determine if two events are independent if we know information about the conditional probability and the probability of the event itself that we're focusing on. Right, so here it is. How do we tell? So I've already stated this now. The first two I've stated. So two or more events are said to be independent if the event of one occurring has no effect on whether or not the other one will also occur. It doesn't change the other one's probability. We look for one of the following equivalent equations to determine independence. So if any one of these three things happens, you would say that events A and B are independent. So again, if the probability of A occurring, given that B has already occurred, if that is just the same as the probability that A occurs on its own, right? The fact that B happened has no effect on A happening. It doesn't change its probability. Then they're independent, and vice versa for line 2. And putting these kind of together, like we'll see more rules, more probability rules later in the chapter. But you could also figure this out. Show this: the probability of A and B occurring, right? Both of them happening at the same time. If that's just the same as the product of them occurring separately, the product, then that's another way of saying that the A and B are independent. All right, so show one. If all three of these are false, if you can't show any of these, then they're dependent. They're dependent events. All right, so they give an example here. Given the following information, can we determine which pairs of events A, B, and C are independent or dependent? So here we are given the probability of the individual events, right? The probability that A occurs on its own is 0.2. The probability that B occurs is 1/2. The probability that C occurs is 0.3. And then we're given some conditional probabilities. The probability that A occurs, given that B has already occurred, is 1/2. Notice that that's not equal to 0.2. If this was equal to the probability of A, then we would say that B occurring has no effect on A. But see how B occurring does have an effect on A. The probability of A occurring on its own is only 20%, but when B happens, the probability of A occurring is 50%. So right there, A and B are not independent. They're dependent events. And they're showing that here. Right. Same thing. Look at this. The probability of B was a half. The probability of B occurring, given that C occurs, is still a half. So over here, C happening first, the probability of B is still a half, just as if it were on its own. So B and C are independent, and they show that here. And then look here, the probability of A occurring, given that C occurring doesn't change the probability of A. The probability that A occurs, given that C has happened, is still 0.2. Right? The probability that A happens on its own is 0.2, and if C happens, the probability of A happening is still 0.2. So A and C are also independent. All right, and you can see that, read through all that here. All right, then the second part of this, and again, you've already seen this, but remember, two events are mutually exclusive if they don't share any common outcomes. So if two events are mutually exclusive, all three of these will happen. All these probabilities will be 0 because they don't share any outcomes. The probability that A happens if B happens, is 0. Because if B happens, that means A can't happen. Remember, A and B can't happen at the same time. So if B happens, A can't happen. Same thing, if A happens, B can't happen. And again, they both can't happen at the same time. You saw this earlier. Probably A and B would be 0. All these would be 0 if events A and B are mutually exclusive. And if one of these is if these are non-zero, then they're not mutually exclusive. That means they would have some sort of events and outcomes in common. All right, so a question related to that. An example, given the following information, what can we say about the relationship between events A and B? So you see here, the probability of A occurring on its own is 21%. The probability of B occurring on its own is 53%. The probability that B happens if A has already happened is 0. That means that A and B can't happen at the same time. That means that A and B are mutually exclusive. All right. So they're saying that here. See, since the probability of B given A is 0, we know that A has occurred and B cannot occur, which means A and B are mutually exclusive. All right. Note that A and B are dependent. Because remember, if they were independent, the probability of B given A would be the same as the probability of B. It would be 0.53. But it's not 0.53, so they're dependent. All right, so we can say a lot of stuff given conditional information. All right, so you can read through example 3. I'll go through some problems. All right, so here, a game requires that players draw a blue card and red card to determine the number of spaces they can move on a turn. So let A represent drawing a red card, right, with 4 possibilities, 1, 2, 3, and 4, this red 1 through red 4 here. Let B represent drawing a blue card, and notice that there are 3 possibilities, right, 1, 2, and 3. The blue card's on top here. If the probability of a player drawing a red 2 on the second draw, given that they drew a blue 2 on the first draw, is this, right? This is probability of red 2 on the second draw, given that they drew a blue 2 on the first draw, is 1 out of 4. What can we conclude about events A and B? All right. Now select the correct answer below. Well, let's see. I mean, the player draws a blue card and a red card. All right. So if they drew a blue 2, they drew their blue card. See how the red cards, they still have 4 choices to draw. The probability of drawing a red 2 is 1 out of 4 normally. All right. I'll write this down. Let me pull up a piece of paper here. All right. In this picture, again, you see the the probability of the person drawing a red 2, because they're drawing a blue card and a red card, right? A blue card first and a red card next. There are 4 red cards and one of them is a red 2, so the probability of drawing a red 2 normally is just 1 out of 4. And the probability of drawing a red card, the red 2, given that they drew a blue 2, is still 1 out of 4, they're saying, right? Because again, you draw one of the blue cards, you still have 4 red cards. Right? So the probability of pulling a red 2 out of those 4 red cards is still at 1 out of 4, which is the same as just earlier, the probability of drawing a red 2. So since these are equal, the fact that you drew a blue 2 in the first card has no effect on drawing a red 2. They have the same probability. Didn't change the probability of drawing a red 2. So drawing a red 2 on the second card and drawing a blue 2 on the first card are independent. Right? This means that R2 there and B2, whatever those events represent, are independent. And I believe that's one of the choices. So yeah, looking back here, this means that events A and B are independent, right? Right here, the third line. Yeah. Let me check to get rid of this paper here. Yeah. Great. All right, here. Given the following information, determine whether events B and C are independent, mutually exclusive, both these things, or neither of these things. All right. So now I'll pull up some paper, and I'll write these down and bring it up on a bigger sheet. Okay, so I've written down those probabilities, and they're asking us, are B and C independent? Right. So I'll ask that first question: are B and C, those two events, independent? All right, so remember what we have to show, what we would have to show. Basically, is the probability of B given C equal to the probability of B on its own, right? Does C, because if they were independent, C happening would have no effect on B happening. So the probability of B when C happens would be the same as just the probability of B happening on its own. Well, the answer here is no. Look, this is 0, and this is 0.6. No, that's not happening. So no, they are not independent. They are B and C are dependent events. And then the second part, are B and C mutually exclusive? Well, we already see this part here, this part here. See, this is telling me, both of these are telling me that B and C have no common outcomes. They cannot happen at the same time, right? The probability of B and C is 0. The probability of B given C is 0. So because of these, the answer is yes, right? The two events are mutually exclusive. They do not share an outcome. So going back to the assignment here, they are mutually exclusive, and that's it, right? They're not independent. The only one of these that applies is they are mutually exclusive. Okay, another problem, same objective. So a fair die has 6 sides with numbers 1 through 6 on each of the sides. Okay. In a game of dice, the following probabilities are given. The probability of rolling 2 dice and both showing a 1, so snake eyes, right, 1, 1, is 1 out of 36, right? Because if you roll 2 dice, there are 36 possible outcomes, 6 for each. 6 times 6, 36. We'll talk about counting numbers of outcomes later in the chapter as well. The probability of rolling the first die and it showing a 1 is 1 out of 6, right? Because that's just the one die. 1 out of 6. If you roll one die after another, the probability of rolling a 1 on the second die, given that you've already rolled a 1 on the first die, is 1 out of 6, right? Those are independent, right? Because if you roll a 1 on the first die, it's kind of like my flipping a coin example earlier. If you roll a 1 on the first die, that has no effect as to what's going to happen on the second roll. None whatsoever. So the probability of getting a 1 on the first one is 1 out of 6, and then the second one is 1 out of 6 as well. I mean, it doesn't change. So let event A be rolling a 1 on the first die, and event B be rolling a 1 on the second die. Are the events A and B mutually exclusive, independent, neither or both? Well, are they mutually exclusive? No, because they can happen at the same time. You can roll a 1 on the first die and a 1 on the second die. And the probability of both those things happening was 1 out of 36. That's not 0. So they're not mutually exclusive. But they are independent. All right, the probability of, they tell us right here, the probability of event B given event A is the same as the probability of event B. Right. So the 1/6 probability doesn't change. So they are independent, not mutually exclusive though. Right. It looks like I got one more here. All right, so this one they tell us something similar. A game show releases its secrets about how it chooses contestants from the audience. They say, the probability of being chosen for the first round on the show is 1 out of 30. The probability of being chosen for the second round on the show is 2 out of 15. So a little different. The probability of being chosen for both rounds is 0. So you can't be on both rounds. Let event A be being chosen for the first round, and event B be being chosen for the second round. Are events A and B mutually exclusive, independent, both, or neither? All right. So they are mutually exclusive because they cannot happen at the same time, right? I can't have A and B happen at the same time. You can't be selected for both rounds. They mentioned that here. The probability of being chosen for both rounds is 0. So they are mutually exclusive. Are they independent? Well, no, because remember one of the if they are independent. Remember this was one rule that would be true if they were independent. I'll write it up here. Remember, if two events are independent, that means that the probability of A and B occurring at the same time would be equal to the probability of A occurring times the probability of B occurring. That's going to happen if two events are independent, along with those conditional probability ones that were mentioned earlier. This one is 0, and this one, the probability of being selected in the first round is 1/30th times, and the probability of being selected in the second round is 2/15ths. That's not true, right? 0 can't be equal to the product of two non-zero numbers. So since this isn't happening, A and B are not independent, right? They'd be called dependent events. One happening does have an effect on the other. Because again, whether or not you're chosen for the first round has a huge effect on whether or not you're chosen for the second round. Right? So they are mutually exclusive because they can't happen at the same time, but they're not independent. Right? So that seems to be the only one that fits. Great, and I believe that is all for my questions. Again, you might see some different ones, but they'll all have a similar feel to them. Be a similar type questions. Are these events independent, mutually exclusive, both, or neither? And you got to know what formulas you're looking at, to determine those things. Okay, so hopefully this is a good, nice guide for you. You can watch this and see how to do certain problems under certain objectives, and hopefully it helps guide you through section 3.2's homework when you do it on your own. All right, and thank you very much for watching.